Hiya. So in today's video, we're going to look at symmetry. So we're going to be basically looking at some histogram, and we're going to see kind of when it's symmetric in some way, in like some nice way. So like for example, when we were looking at a normal curve, so a normal curve we kind of saw is like this, right? And it's always symmetric about kind of this middle part, right? You can kind of flip this around the y-axis and nothing happens, right? So this term symmetric is basically coming from calculus, right? Where you can kind of flip or rotate things and you get a very similar thing. So for example, the normal curve, this is going to be symmetric about the y-axis, right? This is our even functions. So you can just kind of flip it around the y-axis and you're good. Another way to see is the odd function. These are symmetric about the origin. So in other words, I can kind of rotate it around the origin and I get the same function, right? So that's kind of the ways to think about odd and even functions and their symmetry. But what happens in the case of a distribution? When is it kind of symmetric? So if I look at a histogram, so if I kind of take this and I look at like a distribution and I have something like this, we'll do something smaller like this. You can kind of see that I tried to draw, I'm not perfect, but I tried to draw a symmetric distribution. And basically the key point here is that this and this must be equal to another, this and this must be equal to one another, and this must be equal to one another. And so how do we do this? If this is v here, what we're going to say is that our distribution is symmetric about v. So if we have a distribution of x, it's symmetric about this v if we have the following condition, that we have the probability of x is equal to v plus x. So I move kind of in this direction. This should be the same as moving the same amount in this direction, right? So I should do the same in the minus x direction. So this should be probability that x is equal to v minus x. And this should be true for every x, right? For all x. No matter how kind of far I go, I should get the same height in essence, right? And this is where we're kind of doing this. Like this is the same for the normal curve, right? So if I make this v, if I go this way by x and I go this way by x, so minus x for that way, you'll kind of see that I should get, if I did this right, probably not because, I mean, I'm freehanding, I should get the same height, right? So that's the idea here about symmetry. And so the nice thing is, so if we have v is equal to 0, then we get symmetry about the y-axis, right? So you can really think about v is equaling to 0 as being, I can just flip over the y-axis and everything is nice and easy. Equivalently, we can, since with the normal curve, we actually for a while looked at kind of less than or equal to or greater than or equal to, right? Because we're thinking of areas. So like if we're looking at some area here, this area should be the same as this area here, right? And in that case, we can actually define, we can look at these in a distribution, or we can look at this in a inequality kind of way. So we can have x less than or equal to v minus x. This should be equal to the probability that x is greater than or equal to v plus x, right? So we want v minus x, so here's our v minus x, and here's our v plus x. We want x less than or equal to this area, right? This is the x less than or equal to. We want that to be equal to the x greater than or equal to. That's why we're kind of going to the right here. And so that's where this is coming from. And so what we're going to do is we're going to take this symmetry and we're going to kind of use that to help us with summations. But for now, so let's kind of look at where this works out from the summation perspective. So say I have my n random variables, so I take n random variables and I want to sum them up. So I have all my random variables and I get some Sn. And we're going to say that each xi is symmetric about 0. Now remember what this means. Our v is equal to 0, right? So v is equal to 0. So I can just plug in v is equal to 0. So I have p of x equals x. This is equal to x is equal to minus x. So this is basically where this is coming from. And what we have here is that basically this tells us that x and minus x have the same distribution. Well, how do I know this? Well, if I take my p of x is equal to x, well, I can say this is equal to minus x, right? So this is only true when we have this condition, right? We have to assume that xi is symmetric about 0. Well, here, this minus, I can just move to the other side, right? And so here we see that x and minus x are going to have the same distribution. In other words, if we're doing independent trials, then we know that Sn and our minus Sn are going to have the same distribution as well. So the way I kind of like to think about this is if I have my normal table for a distribution, right? So I have some distribution, and you can kind of remember this as, like obviously this is going to be multi-dimensional, but if I only have two x1 and x2, then it's going to be symmetric. So like if these are all some numbers, then the minus version is just going to have the minus signs on this diagonal. So it's just going to be the minus version of everything, kind of. And so yeah, so that's where you get this kind of thing. Yeah, so each xi has the same distribution as minus xi. So then each of the SNs is going to, yeah, so that kind of helps you figure out where this is coming from, right? Because if we want to sum these up, and these, each one has the same distribution as the minus, then if we sum up the minus version, then they're going to have the same distribution as well. It's a little weird. Take some time to think about it. It's definitely a little bizarre. But basically what we're saying here is that since they have the same distribution, then we have that p of Sn is equal to x. This is equal to minus Sn is equal to x. But again, I can move this minus sign over, and I just get that the sum is equal to the minus version as well. Which is kind of bizarre. But what this is saying is that Sn itself is symmetric about 0. The sum is symmetric about 0 as well. So it's a symmetric distribution if all of the parts are symmetric as well. So this video is kind of long here. So I'm going to stop here for now. And we're going to look at this a little further in the next video. So I will see you then.